Hello, this time we continue with our introduction to calculus, sponsored by the Marx Center at UTEP. I'd like to thank Marta Delgado and Maria Barraza for their continued support on this enterprise. Julio Urenda will be your instructor for this session. So I have the following consideration. What is 2 to the pi, right? Well, for this one, essentially, we have no idea what it is. We really don't know. Ultimately, we have developed some intuition on what the power of 2 natural numbers, for example, should be. For instance, we have a clear understanding of what is 2 to the third, because we can simply develop this as a product, 2 times 2 times 2. So when we think of this as the number in the base multiplied as many times as indicated here, of course, we can further this and say, yeah, if we interpret this in terms of a reciprocal, then we can say, yes, if you want to extend the power to an integer, you may say 2 to the negative 3. It's really something that looks like this: 1/2 to the third, then expand on the reciprocal. This would be being 1/2 times 1/2 times 1/2. So at this point, to make this extension, we have to make use of fractions. But what about a fractional power? How should we interpret, for example, 2 to the 1/2, you may say? Well, of course, we have the symbol that indicates that this is the square root of 2. But even with that symbol in place, we have to realize that this is just an invention. Because how is it we define this? Well, 2 to the 1/2 is the unique real number, positive, such that when I square it, the result is 2. We define rational powers in a similar fashion by combining these ideas. But what if it's irrational? Well, I really don't. But what I know from these relations is the following. We can turn any of these exponential expression, for example, the one that is associated with this, which is saying 2 to the third is equal to 8. This one that indicates 2 to the negative 3 is 1/8 into an equivalent version using what we call logarithms, which essentially are associated with the powers themselves. So when I see this, I can equivalently indicate that this is the logarithm base 2 of 8 is equal to 3. This is what I'm saying. When you take a number and you associate it with a logarithm, you're finding the exponent in this case. So equivalently, I can say that the logarithm base 2 of 1/8 is equal to negative 3. Now, following these ideas, introducing the symbol, for example, you may say that the 2 to the 1/2 is interpreted as the square root of 2. Well, that is the same as to say that the logarithm base 2 of the square root of 2 is 1/2. But at this point, we can continue with discussion only with rational numbers. We still have no idea how to interpret this symbol. But for that, we're going to introduce one thing. What is the logarithm? What should be the rules that it should follow? Well, we have seen a few of them. So what is the expectation? We expect that a logarithm respects the following rules. For whichever logarithm that we're talking about, if we multiply, this should expand in this fashion as the logarithm of x plus the logarithm of y. What else? Well, this is basically because we're trying to extend this idea in terms of the rules for exponentiation. That's what it is. It's just a recasting of those rules. And what else? Well, we like this to also satisfy the following. If you take a number 20 powered, this should be n times the logarithm of that number. Of course, there are restrictions that we have to mention, but ultimately, this is what we want to get, right? We want whichever logarithm function that we can define to satisfy these two. And of course, right, taken from the example here, if we associate with base 2, we would say that the logarithm base 2 of 2, well, is equal to 1. And we also have the expectation that the logarithm base 2 of 1 is equal to 0. No? Okay, now, here is my proposal. To extend the logarithm, or the idea of the logarithm, beyond the natural numbers and the rationals and the integers, we're going to introduce an integral. Now, what type of integral? Well, a special one, because maybe we get some recalling from the previous session, we see that the indefinite integral of an expression of this form, of course, I'm taking n to be integer, is equal to x to the n plus 1 over n plus 1 plus some constant, provided that n is different from -1. So the only antiderivative that we haven't considered is the one that is associated with this. What is that? Well, we don't know. So let's investigate. I have the following proposal. I'm going to define for x positive, real number, to be ln of x, and use the symbol for definition, as the integral from 1 to x of 1 over t dt. Now, immediately, just from this definition, just from the definition itself, we get the following. If we take derivatives, we can say, look, if I take the derivative of the function that I'm defining here, this is the derivative with respect to x of the integral from 1 to x of 1 over t dt. And of course, the fundamental theorem of calculus, the second part, indicates that whenever you take this, you turn it into 1 over x, and that's it. You essentially recover the expression that you have inside. So, we say, well, first thing, since x is positive, we have that 1 over x is positive. So the function that we have here is increasing.
on its domain, on the collection of positive real numbers. Okay, so we have an increasing function. So, is it also continuous? Yes, of course, it's continuous because we're defining an integral way, and its impact is differential. Note that ln of x is continuous. That's a free fact, since it is differential. It's defined through an integral. Let's see. Probably the only thing that we have to say is that, well, what would be the behavior of the logarithm? How does it look if we graph it? Well, let's do the following. Oh, by the way, the fact that this is positive and is indicating that it's increasing, it's also saying that if the function that we're defining here has an inverse, as long as we can record the entirety of its codomain. This function admits an inverse. Of course, we need to find the range in order to establish what the inverse is. So, what would be the range of this function that we're just defining? Important thing, defining. Well, it's increasing. I want to know the asymptotic behavior, and that will tell me exactly what's going on. So, in order to get to that point, I'll do the following. I want to investigate what happens to this quantity, the logarithm, as x tends to infinity. So I want to know what is the limit as x tends to infinity of the natural, or of this function that we're defining as ln of x. I want to know what that is, and I also want to know what happens with this expression as x tends to 0. That will tell me how it behaves essentially as it gets closer and closer to 0, and as it just goes without any bounds in the positive direction. The continuity will tell me a few more things. So, well, kind of like a complicated thing, but let's look at this limit first. Let's try to examine it. And if we look carefully on it, we have the following. Actually, I'll even try to graph it to make it a little bit more appealing. So, but the only thing that I have at my disposal is to graph its derivative. It's hyperbola, portion of a hyperbola, right? So I would say, well, that's all measuring here. Now, I'm not going to lose some time because I'm tending to infinity. I really will take x values that are larger than 1. I have 1 here as my reference point. And really, what we're saying is, what happens with the area associated with this as we move further and further into the positive direction? Well, that's a complicated thing. But let me do the following. Instead of considering only the entire area, what we're going to do is consider portions of it. So I'm going to introduce a couple of labels, starting at 1, 1, 2, 3, 4, 5, 6, etc. I'll follow in that direction. And then I'm going to introduce some rectangles. Rectangles that will allow me to bound the limit that I'm indicating here. Now, we examine this. The base of each of these rectangles that I'm defining, it's 1. So the only thing that I have to care about is well, the height of each of them. But, well, a careful examination of the of the coordinates of these vertices of the rectangles says that this one is 2 comma, well, 1/2. Remember, this one is the curve y equals to 1 over x. This one is given in coordinates as 3 comma 1/3. This one, it's given as, well, in this case, as 4 comma 1/4. This one is given as, well, let's see, 5 comma 1, well, not 5, I'm sorry, I kind of jumped. This should be 2, 3, no, that's fine, 4, here, the label, 5, 1/5, so and so on. So look, what we have here is that, for example, if I say that the integral from 1, just to take an instance, from 1 to 6 of 1 over t dt, it's clearly greater or equal. Of course, we have no idea of what may happen, but to the sum of these ones, which would be 1/2, the area of this rectangle, 1/3, the area of this, 1/4, 1/5, 1/6. If we were to continue in this fashion, we would observe the following behavior. We'll just erase this portion. And then we will say, look, once we have this, we can extrapolate what we have and get this. The integral from 1 to n, for n being a positive integer, of 1 over t dt, which is nothing else but the definition in terms of this ln function of n, of the number n, to be specific, and natural. It's greater or equal than a certain sum. Well, what would be that sum? Oh, natural and bigger or equal than 2, of course, to make it valid. That would be 1/2 plus 1/3 plus 1/4 plus 1/5 plus, we'll look at how many terms we have here. Well, there's an association with the number that we write here, and this should be 1 over n. But even that sum that we have there is a little bit complicated to actually determine. But let's examine a few terms of this sum, right? And let's see if we can collect them. So if I have 1/2 plus 1/3 plus 1/4, that will be the one associated with n equal 4. Now, what if I go up to 8? And you'll see in a second why is that I'm jumping in that fashion. Well, look, what I want to do here is group in a slightly different way. Here, I'm going to group these ones, and I'm going to group these ones. Once I make that grouping, I'll observe the following. A fourth is smaller than 1/3. So I can say that this is 1/2 plus, well, 1/4 plus 1/4. In a similar fashion, for this one, I can say that this expression that I have here is greater or, well, greater or equal to 1/2 plus 1/4 plus 1/4. While this one that we have here plus 1/8, if I make a comparison among these ones, I'm choosing the one that is the smallest, and I would say, well, 1/8, 1/8, 1/8, 1/8. Now, why is that the grouping is important in this case? Well, it's because if I group them in this fashion and I make this bounds, then I can say, look, the quantity that I have here is 1/2, but a quarter and a quarter is 1/2. So this is 1. Well, this one, well, this is 1/2. But, oh, sorry, right over here. This one, 1/2, as we just said it, 1/2. But this one, well, it's an 8 plus an 8 plus an 8 plus an 8. Well, that turns out to be 1/2 again. This is 1/2. Ah, now I start to see a pattern here. Look, this is nothing else but 3 times 1/2. This one is nothing else but 2 times 1/2. So, if I make these jumps by powers of 2, I will observe something like this. If I had to look at the integral in terms of the logarithm, remember, this is exactly what we're doing. Let's say at a power 2, like 2 to the 4th, which is 16, you will have integral from 1 up to 16 of 1 over t dt. Well, that would be greater or equal than 1/2 plus 1/3 plus 1/4 plus blah, 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 plus 1 over 15 plus 1 over 6. And then you say, well, let's group things in the way that we just developed here. And we will have that this quantity would be exactly the same as 1/2 plus 1/3 plus 1/4 plus 1/5, then continue up to 1/8, and then plus 1/9, then continue until 1/16. I'm just grouping them. But once I make that grouping, what I observe is that this, well, is bounded below by this quantity, 1/2. Now this one, I'm going to choose the smallest in this grouping, so that would be plus 1/4 plus 1/4 plus, and then here 1/8 plus blah 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 blah. I'm making so many things here that we have to mention. In this blah 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 blah, I'm grouping a certain number of elements. Here I'm grouping 1, here I'm grouping 2, here I'm grouping 4, and in the next one I'm going to group 8. So this one would be 1 over 8, well, 1 over 16, I'm sorry, plus blah 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 blah, plus 1 over 16. But once I make that, look, the quantity that I have here is 1/2 plus, well, 1/2 plus 1/2, well, plus 1/2, which is nothing else but 4 times 1/2. So, oof, that was a lot of work. But look at the thing that we just got from making all these computations. We extrapolate a bit. Of course, we can verify these things using induction and things like that, but we have to gain some intuition of what is that we're doing. Well, if I want to write the function that we just defined now in this fashion, as 2 to the k, right? For k, a positive integer, this would be the integral from 1 to 2 to the k. Let's just extrapolate from what we got from here. 1 over t dt. That has to be, no, let's just make a count. In this case, the power was 4, and we end up grouping this many times 1/2. Well, in this case, we were associating this as an integral from 1 to the power of 2 to the 2. And look, from 1 over t dt. And in this case, look, the 2 is appearing here, the 2 is appearing here. In this case, what we have is an integral, of course, that one, keeping the symbols, make an honest comparison, 1 over 2 to the 3 of 1 over t dt. And from here we get, well, that 3 is appearing over here. That establishes the following. Of course, if you want to be careful, you'll do it by induction, but well, we don't have the time. That this quantity here is less than or equal than, well, that would be k times 1/2. What is the indication for us? This is saying that the limit as x tends to infinity of this function that we just defined in an integral fashion, well, is that. Because as x tends larger, you can find a power of 2 that fits into your estimation and make it as big as possible. Of course, you have to go very, very far beyond in order to get the estimation, but that's okay. We'll eventually get it. In a similar fashion, a very similar fashion, we can also say that the limit as x tends to 0 of this function is that one. So the logarithm is an increasing function. First thing. This thing that we're defining is increasing. Summary. Ln is defined on C interval. It's increasing. Has range. Whole real numbers. Why the whole real numbers? Because it's a continuous function. It has to touch every single one. So, this is something new. Let's do this. Is this function behaving now in the way that we expect? Meaning, does it satisfy the rules that we were expecting? Does it behave like a logarithm should do? Is this logarithm a rule-abiding citizen? Well, let's see. Let's take a look. We have an idea. We're just making assumptions. But let's do the following. Now that we define it in an integral fashion, and we know what the derivative of that should be based on the fundamental theorem of calculus, let's explore the following. Suppose or let A be a positive number. So I'm going to examine the following expression, Ln of AX. I'm just building a new function with the one that I just defined by composition. Then you say, well, whatever you have here should be, by definition, the definite integral from 1 up to A times x of 1 over t dt. Now, based on this, I'm going to take a derivative with respect to x, of course. And then I say, well, what is the derivative of that thing? Well, that's the derivative of ax. Remember, a is fixed. And then I say, well, look, but this is nothing else than the derivative with respect to x of the integral from 1 up to ax 1 over t dt. Boom. Composition of functions. Chain rule. Fundamental theorem of calculus would indicate that this is 1 over ax times a. But then once I see that, immediately elimination. Kill that one, and I get 1 over x. Then you say, wait. What we observed is that this one is the derivative of the function that we defined. Look, so we have the derivative with respect to x of ln of x is equal to 1 over x. Remember, this is just a definition. It's just a naming convention up to this point. And then I say, well, but also the derivative with respect to x of the composition of this function with this linear combination is 1 over x. They're identical. And what do we know about functions whose derivatives are identical? Well, what we're saying here is that these two are antiderivatives of the same thing. They differ by a constant. Well, let's find that constant. So we would say ln of x and ln of ax differ by a constant. Let's find it. So in particular, it would be ln of x minus ln of ax is a constant. What is that constant? Well, let's make our lives easier. And what I'm going to do is use some number that is easy for us to calculate. Look, the integral definition says, for example, that it's fairly easy to calculate the value of this function at 1. Why? Because it would be the integral from 1 to 1. Well, what is that? That is 0. But let's state it over here. Look, note that ln of 1, by definition, is the integral from 1 to 1 of 1 over t dt. But look, this is just a point. It defines no area, so this is equal. Since we're looking for a constant, this expression should be constant regardless of the value of x. Well, let's input one that we know. So we say ln of 1 minus ln of a times 1 is equal to that constant. Well, this is 0. This one is the function that we're looking for evaluated at a. That means that the constant is this. But if that is the constant, well, let's just write it. We would say ln x minus ln ax is equal to negative ln a. Maybe this is not something that we have seen, but look, what I'm going to do is just recast this equation that we just obtained from this computation into the following. Ln of x plus ln of a is equal to ln of ax. I'm going to recast it into more familiar terms. This would be ln of ax is equal to ln of, well, xa plus ln x. But x is arbitrary. It could be whatever you want. So, of course, within the domain of what we're saying, for x equal to b, we get, of course, b positive, right? We have ln of a b is equal to ln of a, it's ln of b. Boom. First rule we were expecting. Second rule. Does it behave in powers? Well, let's see. Kind of the same story. What I would say, take the integral definition. I want to see what is the behavior of this thing. What is ln of x to some rational power? Now, it's important that I'm taking rationals because I have absolutely no idea what a number to an irrational power is. I know how to interpret this. And the interpretation, when x is positive, is that I have to make a power and then take a root. I can do that, right? Because I have the ability to take inverse functions and things like that. So, what is this thing? By definition, this is the integral from 1 up to x to p over q of 1 over t dt. Now, this one was very successful. This comparison, I will do exactly the same thing, hoping that I get what I want. Well, let's take the derivative of this. This is d dx of ln of x to the p over q. And well, this results into the following. This would be d dx of the integral from 1 up to the x over q, 1 over t dt. Then you say, well, wait a second. Fundamental theorem of calculus, composition of functions, chain rule, boom, we get the following. 1 over x to the p over q times p over q times x to the p over q minus 1. And you say, well, why is that you're allowed to do this? Again, we're taking inverse functions in order to allow us for us to be able to compute these things. But then you look at that expression and it looks very familiar. Look, this is just p over q times x to the p over q minus 1 over x to the p over q. Simplification of this leads to p over q times 1 over x. So what is this saying? Well, it's not exactly the same as the antiderivative. I mean, as a derivative of the function ln of x, but it's pretty similar. It differs by a constant factor. So look, what this is saying is that the derivative with respect to x of ln to the x p over q is the same as the derivative with respect to x of the function p over q times ln of x. Remember, when we have a constant multiplying a function, we can take it out of the derivative sign. So, that means that since these two are equal, and equal to p over q times 1 over x, well, this is saying that these two functions that we have here differ by a constant once again. So, say it one more time, and in fact, I'm going to say it here because it's exactly the same thing. So, we have ln of x to the p over q minus ln, well, sorry, p over q times ln of x is a constant. What is that constant? Well, we'll evaluate this expression on a known value. And well, we cannot evaluate it at 0 because that's undefined. We can evaluate it at 1, but if we evaluate at 1, we get this. Set x to 1 to find that constant. And we get ln of 1 to the p over q minus p over q times ln of 1. Well, 1 to any power is 1. So this expression that we have here turns into ln of 1 minus p over q times ln of 1. ln of 1, the way that we define it integrally, it's 0 minus 0. So this is 0. That means that the constant that we have here is really 0. But if that constant is really 0, we get ln of x to the p over q is exactly the same as p over q times ln of x. And boom, the second rule. Then you say, it satisfies those rules. But if we return to the original place where we said, well, 2 to the 3 equal to 8 is an equivalent way of saying that the logarithm base 2 of 8 is 3. Well, here we have to indicate a new element, the 2. But the 2 in this expression, look, is associated with the following equation. 2 to the 1 is 2. So that would say that the logarithm base 2 of 2 is 1. In other words, when you take the logarithm, whichever base that you're associating with, well, it should return a 1. So the question is, if this looks like a logarithm, what is its base? Well, I'm going to put quotations here because it's not a logarithm yet until we define those things. But that one turns out to be based on the consideration that the function is increasing. Look, it starts at 1. So this ln of 1 is 0, but it's increasing, and it's increasing without bounds. So at some point, it has to cross 1. It's exactly what the number e is. E, the base of this logarithm function, is the unique solution to the equation integral from 1 to x of 1 over t dt equal to 1. If you want to think of this in terms, in kind of graphical terms, in geometrical terms, you would say that E is the unique number for which the area beneath the curve y equals to 1 over x from 1 to that number is 1. And we'll take a geometrical interpretation of this number. Of course, we know certain approximations, well, which are really a theme for a subsequent video. But that is the definition of E that we can provide. Now, you would say, at least give me some intuition of what that number is. Just don't throw it to me. Yeah, we can provide a few things using trapezoids. So we know that the number is there. It exists. But can you give me at least some bounds of what is it? Yes. We can do some bounds. Let's do some bounds. I will say, by looking at this graph, just to get some geometrical intuition. I know that the number is there. It's just that I don't know which one is it. But look, what I know is that this, whichever it is, it has to be something that looks like the following. What if I make a comparison with 2? Well, let me make a comparison with 2. I don't know what that number is or where is it located. Well, let's make some rough comparisons. That's how things start. What if I put that one? Well, I'm going to overestimate the area by dropping a line that joins these 2 points, 1, 1, 1, 1/2. Now, since this function is concave up, it's guaranteed that this line that I'm dropping here, it's exactly on this region above this graph. So that what this is saying is that the area associated with this trapezoid is larger than the area beneath the curve. So let's do the following. What is the area of the trapezoid? Well, fairly easy. Here we have a base of 1, a base of 1/2. In the area of a trapezoid, let's recall this is an area of trapezoid. It's given by larger base plus a smaller base times height. Well, but that height divided by 2. So, well, let's see what this number is. Multiply here, we have, well, 3/2 over 2, that's 3/4. Okay, so this area that we have here, which is another estimation, is 3/4. Well, that means that the integral from 1 to 2 of 1 over t dt is less than or equal than the area of the trapezoid, which is 3/4. But this is saying, in virtue of the fact that this function that we're defining here in terms of an integral is increasing, that this is established. This must happen. 2 is less than e. Now, can we bound it in a different fashion? Yes. Let's establish an upper bound. Let's establish an upper bound for that number. At least so that we have an intuition of where to locate it on the real line. Well, it was very successful to do this. So what I'm going to do now is to construct another trapezoid. But now this trapezoid is going to be below the curve. And I just have to jump a little bit, not too much. One more time. So, starting at 1, 2, 3. Okay, now I'm going to make an approximation, but an approximation based on a tangent line. Tangent to the point on the curve y equal to 1/2. I'm sorry, not 1 equal to 1/10, but y equal to 1 over x at the point 2, 1/2. Well, we know how to do this thing. This is just a tangent line problem. The thing is that what I'm going to do is once I determine that tangent, I'm going to drop it just like that, create a trapezoid, measure the area, and make an estimation. Now look, let's do the following. I would say, let's find an equation for a tangent line. Okay, well, let's see. I'll look at the curve. I'll take a derivative, and the derivative of that would be 1 over x squared. So that means that the slope of the tangent line evaluated at 2 would be, well, -1 over 2 squared, which is -1 over 4. So I have the slope of the tangent line, and I have a point. So I have the line. Now, let's see. This would be y minus, using the formula, the points of formula, y minus y1 equal to m times x minus x1. Of course, we just recast whatever information that we have on this picture, and we get that y minus, well, second coordinate 1 over 2 is equal to -1/4, which is the expectation. We have the line here. This is a degree. This function 1 over x is decreasing, so we expect that the tangent to be the slope of the tangent line to be negative. That's exactly what we get. And in fact, it has to be below that curve, just based on the concavity of this function that we have here. So let's see. Once we have this observation, we have x minus 2. Of course, we just develop this a little bit, and we have equivalently y minus 1/2 is equal to -1 over 4 times x multiplied plus 1/2. I'm going to add, and I have y is equal to -1/4 times x plus 1. That will enable me to find this point by simple evaluation. So what are the coordinates of this point? Well, the first coordinate is known, it's 1. But what about the second coordinate? Well, the second coordinate is y of this function that now we declare it in this fashion, evaluated at 1. Well, that would be -1/4 times 1 plus 1, which is, well, in this case, 3/4. Oh, so now I know the second coordinate, 3/4. What about here? At 3, same story. The point that I have here that is a little below, it's 3 comma. Let's see by the approximation that we have. y evaluated at 3. This is negative 1/4 times 3 plus 1. So this is 1/4. So this is 1/4. So what does that mean? That means that the area of this trapezoid, well, we know the length. This is 2. This one here, which is the height, really, it's a tilted trapezoid. This one is 3/4. This one is 1/4. So we get this area of trapezoid. Let's declare it. Bigger base, 3/4, plus longer base, I'm sorry, smaller base, times height, divided by 2. This one is 2. Sorry, 1. Sorry, 1. So that is 1. What does that mean? This area is 1. But the area below the curve from 1 to 3 is strictly greater than 1. Or at least you can say it's greater than 1. So I'm going to recast it here. And I would say the integral from 1 to 3 of 1 over t dt, it's, well, in this case, greater or equal to 1. And what is that saying in terms of e? Well, by the increasing nature of this function, by the definition, we impose that bound. So now we know that whatever that number is located between 2 and 3. Of course, you can provide better approximations, but again, this is not the intention of this session. The intention of the session that we have here is to define things properly, so that we can, whenever we need, go back to them and start building on those solid definitions. So I think we're almost ready, because now we can start defining a few things. Look, we know what the base of this logarithm is. It's a number. Well, now the number e. That number e is between 2 and 3. Its existence is guaranteed by this construction. Now, we know that this function has an inverse. Let's give it a name. And in fact, let me just combine a few more things here, because we define ln of x as a function. I'm going to just drop that to just provide a name. Ln to be a function from the domain 0 to infinity to the entire real line. Well, so that means that the inverse will just reverse the relation, and we're going to give it a name. Call it x, for what we are really looking for, the exponent, as we are trying to invert the logarithm. So now x would be a function increasing as well, because the inverse of an increasing function is increasing. Now from negative infinity to positive infinity to 0 to positive infinity. Now, what are the properties of this x? Well, being the inverse, it satisfies the following equation. So we have ln of x should be x, right? By definition of inverse. But taking derivatives, you would say, I take the derivative of this expression, dx of ln of x is equal to d dx of x. Of course, this returns 1, but this one, well, composition, right? Chain rule. We have, well, the derivative of this evaluated here. So that's 1 over x of x times the derivative of that thing, whatever that is. I'm just going to write it. X is equal to 1. Cross multiply, look, that's the beauty. Whatever we have here is positive. So this indicates that x prime, the derivative, is equal to x. So it's its own derivative. It's its own derivative. And look, since we're saying that the ln of e is 1, this is the same as to say in terms of inverse functions that e to the power of, oh, sorry, yeah, to the 1 is e. And we're also saying, for example, that I'm just trying to recast a few things. Yeah, that's it. That's all that I want to say. Because with this in mind, look, the function that we have here, it will take another session to explore its properties. But it's increasing. But it's not only increasing, it increases at its own rate. So it really grows fast. In comparison to the other function that we started with, the ln, it's increasing, but it's increasing very slow. This is a typical expectation. If you have a function on one side that is increasing really fast, its inverse is going to increase really slow. Kind of the intuition that we're building just from here. Now, next thing, because I really wanted to class it in terms of how do we define these powers, right? Well, let me make the following. Let me just make the following. Now that we know that the inverse is there, it's defined, it works well, let's examine a few things. If I was to write 2 to the power of 2, of course, you know this is 4. But I want to use this notation that we just invented here to be able to express that. And we can do it. How? Well, what if I say this? You know, I would say that if I want to exponentiate, I want to somehow be able to express this in this fashion. Look, what if I somehow, I'm just inventing some symbols, but this is the general intuition that we want to gain. If I want to write this, what if I want to write it in terms of e, the number e that we just know it exists? Well, e raised the 2 times ln of 2. Now this exists. This one exists. And this one doesn't exist. But we can make it exist. We can just say, well, x of 2 ln of 2. The question is whether this one that we have here is exactly this. Well, let's verify it. We know that this one satisfies certain rules associated with powers. So what I have here is x of ln of 2 to the 2. I know what 2 to the 2 is, but more than that, look, this thing that I have here is the inverse of that. So I can recover this. Even more important, look, what I have here is that it doesn't matter what I write. If I have this x of some number, rational. And I write it in this fashion, well, as long as a is positive, right? So that means this makes sense. I can write this as x of ln of a to the p over q, which now I can compose as a to the p over q. So what is this saying to us? This is saying that the function that we're defining here is a new one, coincides with this one on rational numbers. So x p times q ln of a is equal to a to the p over q for pq rational. Well, whenever two functions coincide on rational numbers, there's a unique extension to continuous functions. Well, what would be that unique extension? The only one that it could possibly be. This one. X of, well, now I can use any number, x times ln of a, or x real, n a positive. So now we define a to the power of x to be that function. So now you wonder, what in the world is 2 to the pi? Well, now we can do it, because now we have a unique continuous extension based on this idea. 2 to the pi is equal to the inverse to the logarithm evaluated at pi times the logarithm that we define integrally at 2. And with this, we conclude. See you next time.